We're surrounded by this vast, invisible world of energy every single moment of our lives. Today, we're going to pull back the curtain on what that world is and how our brains manage to turn just a tiny, tiny slice of it into the rich, colorful reality we experience every day. So let's start with a big, kind of wild question. What if the vibrant world you see, that bright blue sky, the green grass, is just a tiny fraction of what's really out there? It might sound like something out of a sci-fi movie, but honestly, this is the fundamental reality of how we perceive the universe. The key to unlocking this invisible world lies in something called the electromagnetic spectrum. Now, just think of it as the complete family tree of all light, both the parts we can see and, more importantly, all the parts we can't. So what is it exactly? At its core, the electromagnetic spectrum is just a way of organizing all the different types of light energy. Imagine waves at the beach. You can sort them by their wavelength, the distance between each wave, and their frequency, which is how often they crash on the shore. Well, it's the exact same idea for light. And this lineup is huge. On one end, you've got these long, lazy, low-energy radio waves carrying our favorite songs. Then we move up to microwaves that heat our food, and infrared waves that we feel as heat. Right there, smack in the middle, is that tiny sliver we call visible light. And then on the other end, you get the really high-energy stuff, ultraviolet light that gives you a sunburn, X-rays that let doctors see right through you, and unbelievably powerful gamma rays from deep space. Okay, so now let's zoom way in on that one tiny part of the spectrum our eyes are actually tuned into. This is our small personal window onto the entire cosmos. It is so hard to overstate just how small our little window of sight is. All the colors of the rainbow, from the longer waves of red all the way to the shorter waves of violet, are crammed into this minuscule little band. Everything else, all those radio waves, all those X-rays, is completely invisible to us. And here's the part that's going to blow your mind. Despite their massive differences in energy and wavelength, every single one of these waves, from radio to gamma, travels at the exact same speed in a vacuum. This number right here, the speed of light, is the universe's ultimate speed limit. It's the one constant that ties this whole invisible rainbow together. All right, so we've established there's this tiny little band of light that we can actually see. But how does our body translate those specific waves into the experience of, say, a red apple or a blue ocean? Well, the answer lies in the incredible biology of our eyes. This is really the heart of it, isn't it? It connects the physics of light to our actual personal experience. Because here's the secret. Light itself doesn't have color. Color is an interpretation, a story that our brain creates from the signals it receives. So how does that even work? Okay, so inside the back of our eyes, in our retinas, we have two types of light-detecting cells. First are the rods. They're like our night vision specialists. They're incredibly sensitive, but they only see in shades of gray. That's why a room looks black and white in the dark. And then you have the cones. They need bright light to work, and they are the heroes of our color story. We have three types, one for red, one for green, and one for blue light. And our brain just mixes their signals to create every single color we can possibly imagine. Knowing how our eyes see color is one thing, but how do we actually create it in the world around us, on our screens and on paper? Well, it turns out there are two fundamentally different ways to do it. So check this out. On the left, we've got additive color. This applies to things that make their own light, like your phone screen. It starts with black and adds red, green, and blue light together. And if you add them all at full blast, you get pure white light. Then on the right, you have subtractive color. This is for things like paint or ink. It starts with a white surface and uses pigments, cyan, magenta, and yellow, to subtract or absorb light. The more pigments you mix, the more light gets soaked up, until you're left with black. All right, let's broaden our view again. It's not just about color. Light is constantly interacting with every single object in our world, and those interactions determine exactly how we see them. The way materials handle light usually falls into three main categories. First, you have transparent materials, like a clean window that let light pass straight through. Then there are translucent materials, like frosted glass. They let some light through, but they scramble it all up, making things look blurry. And finally, you've got opaque materials, like a wooden table, that don't let any light through at all. They either absorb it or reflect it back. This interaction with surfaces leads to some really clever tech, like polarized sunglasses. So here's how it works. Light from the sun normally vibrates in all directions, but when it bounces off a flat surface like a road or a lake, it gets organized, vibrating horizontally. That's what we see as glare. A polarized lens is basically like a tiny vertical fence for light. It only lets the vertically aligned light through, which blocks all that horizontal glare. It's a really simple but super effective trick. And that brings us to a final, pretty fascinating question to leave you with. We've seen this enormous, invisible world of light all around us, so why? Why did our eyes evolve to see only this specific, narrow window? Is it just some evolutionary accident, or is there a perfect reason for it? It's a puzzle that really reminds us that what we perceive as reality, well, that's truly just the beginning of the story.